Jan Machacek. I will do the first part of today's workshop, the presentation, and then later Patrick will take over and introduce some more advanced aspects of NUMGEO. So for myself, unfortunately, I don't speak Spanish. I only speak English. So whenever I'm too fast maybe, or something is not well understood, feel free to interrupt me at any time, and then I can repeat, or maybe someone can translate. As for today's workshop, I will start with a small presentation introduction to NUMGEO to give you an overview about the features, maybe 20 minutes or so. And then we will proceed with a hands-on. So we will look at the quite simple application, but that showcases already how to use NUMGEO, how to create a geometry, how to set up a model, and how to run it. So with that, without further ado, I will start with the presentation about the overview, about the features of NUMGEO. Maybe first we start with the features itself, just a few background information. So I started creating NUMGEO in 2017 during my PhD studies. And just 2 years later, Patrick joined me in the development. And since then, so it's now, already 6 years joint work on that program. During the time, especially when our positions changed, now we're supervising PhD students. So there are a lot of people contributing now beside the two of us to NUMGEO, which are also listed here from different universities. So currently there are 3 universities working on NUMGEO, which is in Darmstadt, in Weimar, and in Bochum. So all 3 universities are located in Germany. So we have 2 different homepages. Let's say one is the general NUMGEO homepage that you can see here below, or follow the QR code, which brings you to the page where you can download NUMGEO. And then we have an extensive HTML documentation that you can also access that helps you using NUMGEO. So NUMGEO builds on 3 main pillars. The first one is the many different finite elements that are implemented. So these elements, they dictate the physics that can be captured in the simulation. So we have various multi-phase formulations. So you can start modeling the soil, let's say, in a dry state. So that's, let's say, the simplest possibility that you have. But you can also use it or model it in a saturated state. And for the saturated state, we have different element formulations. One is the well-known UP formulation, where you discretize the solid displacement, U, and the forward pressure, P, at the node. So these are the unknowns that you're solving your simulation for. So this is the formulation that is implemented in almost all commercial softwares, like Plaxis, Midas, Z-Soil. So this is the main formulation used in geotechnics. But we also have other ones. For example, we have a so-called U formulation, where the small u denotes the displacements of the solid or the soil, and the capital U, the blue one, denotes the displacement of the water. So instead of discretizing the forward pressure, here we're discretizing the displacements of the water. Now this formulation is especially suitable, for example, if you want to model suction buckets, so suction caissons, or you have dynamic loading of a saturated soil, of a soil with a very high hydraulic conductivity, and at the same time high frequency. For example, if you have a vibrating foundation with up to 25 or 30 hertz, this formulation could be interesting. And of course, you can combine both formulations. Then you have the so-called UPU formulation, where you have the solid displacement U, the pore water pressure P, and then the water displacement U. So these two formulations, usually you don't find them in other software. So these are quite unique in NUMGEO. If you want to increase the complexity a bit, and also obviously, let's say, come closer to reality, you can model the soil as a three-phase material, so unsaturated soils, basically. The UP for negative pore water pressure will be interpreted as a suction, and then you have a partially saturated soil. So this, again, is the formulation that is employed in most commercial software. But it has a drawback. The drawback is that you don't have any control about the pore air pressure. So, for example, this formulation is not well suited if you want to model tunnel blowouts, for example. So for this, we have another formulation, the so-called UPP formulation, where we have, again, the solid displacement, the pore water pressure, but also the pore air pressure. So here you have control of the pore air pressure, which gives you a bit more possibilities of problem types that you can model. But obviously also, it's a bit more expensive than the UP formulation. So for most geotechnical practical applications, the UP formulation, the simplified modeling approach here, is just well enough. So based on these formulations, we would develop also extensions and new equations that describe better the physics of soils that have a residual air and also of expansive soils. So this falls clearly in the range of research, but was also performed in the framework of NUMGEO. So all these formulations, you can use them in static or quasi-static simulations, in transient cases, but also in transient dynamic cases. So for example, for earthquake loading. And this holds also true not only for the saturated case, but also for the partially saturated formulation. Now, the one thing are the formulations, so the equations that we have implemented, but obviously, when we are talking about the finite element method, we also need to discretize our domain, and for that we have various different element shapes and integration rules implemented. Just to give you a quick idea, you can perform plane strain simulations, which are the ones in the top row, so they just give a small excerpt. You have linear triangle elements, quadratic triangle elements, and then you have the rectangle elements, again, linearly interpolated or quadratically interpolated, with different integration rules, as you can see, fully integrated, but also with a reduced integration. The same holds true for axisymmetric simulations. So these are it's the second row that you can see here. And obviously, you can also create 3D models. Again, we have elements, linear elements, but also quadratic elements. Here you can see them in the serendipity formulation or in the full Lagrange formulation here on the right-hand side. In addition to the hexahedral elements that you can see here, we also have tetrahedral elements for the 3D mesh creation. Whenever you have coupled element formulations, so you discretize not only the displacement of the solid, but also the pore water pressure or the pore air pressure, usually you have some requirements for stability to fulfill. And for that, we have implemented Taylor-Hood formulations, but that where you discretize the pore water pressure, for example, only at the corner nodes, and the solid displacement at all 6 nodes. So these elements are stable under various different loading conditions, but they necessitate the use of quadratic elements, which in some cases is maybe not favorable. So we also implemented stabilized linear elements, which discretize with the same order of interpolation, the solid displacement and the pore fluid pressures at the nodes. Now, so the second core feature of NUMGEO are the constitutive models that are implemented. Especially for soil mechanics, having constitutive models that accurately describe soil behavior is mandatory if we really want to have a good prediction of our problems at hand. So we started implementing also, let's say, basic elements like linear elasticity, Mont-Coulomb, modified camp clay, Matsuko-Nakai, Drucker-Prada, or a general plasticity model that can be tuned to either of the aforementioned ones. So these are more practice-oriented constitutive models. For example, the Mont-Coulomb model, very well suited for the strength reduction if you are interested in the factor of safety of a geotechnical structure. But the core feature is rather the big library of advanced constitutive models that we have implemented in NUMGEO. So you can see here now the blue box, which gives you an idea about different constitutive models that we have implemented for sandy soils. So these are models of the hypoplastic family, so hypoplasticity with intergranular strain or with intergranular strain anisotropy, elastoplastic models like the ESA sand model or different model versions of the sandy sand model family, and also hypoplastic models for unsaturated sands and soils. So these models, they are very well suited to capture the highly nonlinear behavior of soils, taking care of density dependency or void ratio dependency, stress dependency. All of them have included a critical state, and they are all also quite well suited to model cyclic loading. So for clay type soils, we have another set of constitutive models implemented. For example, the Avisa model by Merita Tafili, the ESA clay model, the clay hypoplasticity by David Magin, and again, a hypoplastic model for unsaturated clay type soils, and a hypoplastic model for expensive soils. Now, on top of these models, we have special models created or implemented that are or that have been formulated to capture the behavior under high cyclic loading. So when I'm talking about high cyclic loading, I'm talking about hundreds and thousands of loading cycles that are applied to a soil. For example, if you consider offshore foundations or train tracks, then they are not only subjected to a few hundred loading cycles during their lifetime, but to thousands and millions of loading cycles. And these loading cycles usually have a very small amplitude. So this is quite a different type of cyclic loading compared to what we're usually looking at if we're looking at cyclic loading, for example, in the context of earthquake engineering. And for these type of models, we have special high cycle accumulation models. We have one for sand and one for clay. And these models, they take care of the behavior under this high cyclic loading. We need to couple them, these models, with conventional constitutive models that are better suited for the monotonic and low cyclic phase or loading cases. And we couple them with the hypoplastic models and also with sandy sand models. Now, apart from the constitutive models that interrelate the stress with the strain, we need obviously also different or more constitutive models if we want to model soil, especially once the soil is saturated or partially saturated. So for that, we need soil water retention curves or saturation suction relations, depending on which term you want to use. And for that, we implemented, let's say, the industry standard models like Brooks and Curry, Wangenhochten, Fredland and Xing, which are well suited for single wetting or drying curves. But we also have models like the Karlsruhe model or Gao model, which also take care of hysteresis during cyclic drying and wetting, and also incorporate the effect of the change in the volume or void ratio during these cyclic drying and wetting curves. On top of that, we implemented different types or models to take into account the effect of the decrease in hydraulic conductivity once a soil is getting partly saturated. So for that, we have implemented different, let's say, industry standard models like the Brooks and Curry model, the Van Genooten model, and also the NUMGEO model, which are quite widely used. Once your soil is partially saturated, you will have to choose a way to calculate the effective stress. And the most widely used one is generalized Bishop effective stress, where the Bishop parameter, that is a parameter that scales the contribution of the suction to the effective stress, is set equal to the effective degree of saturation. So this is, for example, the model that is also implemented in Plaxis or in set soil. But in addition to that, we have also implemented a bit more advanced ones like the Liu and Likos model, or you can neglect completely the effect of suction on the effective stress, which will then lead you to a net stress approach. In terms of the permeability, you can assume a constant permeability, isotropic or anisotropic, but you can also incorporate porosity dependency by using the Curso-Kalman equation. Now, the third cornerstone of NUMGEO are different and quite advanced contact or algorithms that are implemented. So we have, let's say, the very classical contact algorithm implemented, which is a node-to-node contact. That's the industry standard for geotechnical software, at least. But on top of that, we have a bit more advanced one, which is the Mursal method. And for this, you can choose between two different types, like the element-based or a segment-based approach. And what makes them so special, especially compared to the node-to-node contact formulation, is that you can model quite large relative displacement. So if you have shearing in an interface where the shearing displacement is quite large, these Mortham methods are much better suited compared to node-to-node contact methods. And also these Mortham methods, they reduce the mesh dependency. So there is no need anymore for conforming meshes, as we will see later in the application example. Now, whenever you define a contact, you will also have to define how the two bodies will interact with each other. So for that, we have implemented different options. So you can define such an interface either to be rough. That means you would glue these two interfaces together. They could be frictionless, or the friction would follow a Coulomb friction law, where you have a threshold for the shear stress that can act in the interface. But on top of these basic contact models, we also implemented some advanced contact models, and they allow you to use some of the continuum models that we use to describe soil behavior in the continuum in the interface. For example, you can use the Sand model or the hyperplastic model or even the high cycle accumulation model in the contact formulation to describe the behavior in the interface between a structure and the soil. Now, obviously, every finite element code needs also boundary conditions. So you can apply directly boundary conditions, meaning displacements, velocity, accelerations, pore pressure, pore air pressure. They can be constant or time varying. They can even vary in time and space. On top of that, you can also apply external forces and stresses. For example, just to give you a few quick examples, it's not a complete list, but you can use compliant base boundary conditions. That's boundary condition that you can use to apply an earthquake loading. And if then the earthquake or the waves travel to the top, let's say we have a one-dimensional soil layer, what would happen is that the signal will be reflected at the top, travel back to the base. And if you have not a proper boundary condition, this signal will be reflected at the base again and travel back to the top through the soil column. And obviously, usually, if this is not a bedrock at the base, we want to prevent that because the waves could, in reality, travel through the base of our model. And this can be prevented by using such compliant-based boundary conditions. We have special boundary conditions to determine unknown seepage phases. So if you have an infiltration problem, here, for example, depicted for an embankment, where the seepage line is unknown, and you're looking for the seepage line, so you do not know what the seepage phase will be. We have special boundary conditions that iterate that for you. Quite a new feature, and growing also in terms of the implementation. So we are just at the beginning here. We are improving on that. Currently is the possibility to consider random fields. So for example, you could have random fields for the void ratio, so the density, or soil properties like the friction angle and the cohesion. So there are two approaches that are implemented. So one is inbuilt, that's quite easy to use. It's just one command in the input file, and then you will create a random field that will generate a distribution, a random distribution of soil properties within the minimum and the maximum value for these soil properties, and respecting a prescribed correlation length. And the second approach is an external approach, which gives a bit more options, but is requires the user to use an additional program. Now, if the inbuilt features of NUMGEO do not fit the requirements for a given simulation, one can extend NUMGEO at predefined interfaces. So, for example, you could add your own constitutive model for dry and saturated soils, but also for unsaturated soils. You could change contact properties by your will. You can also define or code your own loading scenarios and boundary conditions. So it's quite extensible at predefined interfaces. Now, NUMGEO, in terms of the pre-processing, how NUMGEO works is it takes an input file, which is a text file that you can see here. People that are familiar with Abacus, that have used Abacus in the past, will recognize the structure of this input file, which is very, very similar to the one from Abacus. To create a mesh, you could use open source software, for example, Salome or Dmesh, and use then a Python script to convert it into the format that we need in NUMGEO to work with. Once you have created such an input file, you can start the calculation, and the post-processing is then usually done in ParaView, as you can see here. So ParaView, for the ones of you who don't know ParaView is a very capable post-processing tool, which is open source, free to use for commercial, but also for academic purposes. And so we're quite happy with that. It's very, very powerful in terms of the post-processing capabilities. Now, obviously, for the pre-processing, that is not a very elegant way, especially if you want to model something quickly, because getting used to that, let's say, input style language, it takes some time, and it also takes time to code that. So we're currently improving on that. And we're interfacing NUMGEO into the preprocessor GID so that we can leverage the cut features and matching features of GID, and that we can offer you a guided way of creating such a finite element model. And then you can run NUMGEO from inside GID. And so the current state is that you still need to post-process your results with ParaView, but we're currently working on integrating also the NUMGEO into the post-processor of GID. So we're currently facing a couple of issues because GID does not support, let's say, element output on on meshes with different element types. So if you have triangular elements and rectangular elements in one model, GID is not able to show these results. So we are in contact with Simno, which are the developers of GID for that. And we hope that we can resolve that in the near future. So for the GID integration, I guess that a couple of you will already know GID, at least the last time that we presented. For some of you in the audience, some of you had already used GID. So for some of you, it's I think familiar. For others, it will be quite new, but we will see how it works in a minute together. I will give you a quick demonstration on that one. Basically, the GID is like any other finite element software, has a sketch area. It has some sort of a data tree, and that is a NUMGEO specific data tree that you can see here. And then some toolbars gathering all the different tools and options that you need to create a model, to mesh the model, and so on. So how do we design the GID interface? Well, it is designed in a way that you can follow, let's say, a path. So this toolbar is created in a way that you start at the top and you work your way down, and then at the end you are able to start your simulation, so that you have some sort of a guide when you create your models. It is also implemented, or in a way that we try to hide the information at the beginning and you expand it when you need it, so that it's not too cluttered at the beginning. It is also implemented in a way that we only show the information, or try at least to only show the information that is really required. So for example, when you're modeling a dry soil, you have only one phase that you're considering, so the solid, so the soil grains. So what you need to find then is the density of the soil. You need to have a stress strain, so the constitutive model, stress strain relation. And then when you want to model, for example, strength reduction, or you want to apply Rayleigh damping, there are some additional settings, but for usual simulations, they don't need to be touched. But what happens now if you want to model a saturated soil? Now, in this case, you have two phases, because you have the soil with the solid grains, and in addition to that, you also have the water. Well, now you also have to give information about the permeability of the soil and the bulk modulus of the water and dynamic viscosity. And things become even more complicated if you have an unsaturated soil, because now you also have to give have the air, and then you have, for example, something like the saturation suction or soil water retention curve that you have to choose another model on. But these things will only be visible when you change the number of the phases. We also tried to make these advanced constitutive models a bit more accessible, to give a well-defined interface for each of the parameters, also for the more advanced constitutive models. Now, what is also offered is that you can easily assign boundary conditions, loadings, materials, or initial conditions to different parts of the model. But I will show that in a minute as well. In addition, so for a lot of features, we have set some default values that work well for most problems that you're looking at. But you also have access to them. You can change, for example, the solver that you want to use. You can change the time incrementation of your automatic time incrementation in one loading step. So there are a lot of options that can be changed, but usually default values work also quite well. So with that, we come to the end of the overview. I wanted at this stage to give you a quick look, at least at the HTML documentation, for the ones of you that have not already had a look on the documentation itself. So I will just quickly share a different screen. So let me see, maybe I have to unshare a minute and then reshare. So let me see. So I hope that you can see my screen and the documentation now. So maybe you could just confirm.
Yeah.
Can you see?
We can see your screen.
Okay, thank you. So when you so usually I think that you're landing on the main page of NUMGEO. And so if you want to download the software, you can go to downloads, and then you just have to fill out a form to this, and we will send you the executable or a link to the executable, and you can immediately download it. And if you want to access the documentation, you just scroll down a bit, and then you can click the link to the documentation, which will bring you directly to the documentation. The documentation will give you quite some insights into different parts. So it will give you detailed installation instructions depending on the operating system that you want to use. So I would say that 99% of the people using NUMGEO are using Windows. A few are using Linux. So for Linux users, we offer currently Ubuntu support. But we try, at least if there are people using other distributions, that we can build for them a different Linux distribution as well. The recommended installation process for Windows is to use the Windows portable version. So there you just download a set of files, and you have not to install anything. You just use the files that are there. Everything that you need is shipped with these files. So that's the way that we would recommend installing and then using NUMGEO. On top of that, if we go back, we have a lot of tutorials. So if we have a look at the tutorial site, you see that there are very simple tutorials giving instructions on how to perform element test simulations. For example, another metric compression test. There is a guide, a detailed guide on how to set up input files to create such simulations. But there are also more advanced examples. For example, an example of transient C page through an embankment, about model creation, model setup, and then even some parts, for example, for the vibratory pile driving. If you're interested in modeling pile driving, you can see how we did it, and you have access to all the files and can try to follow it and learn how to do these more advanced simulations. If you want to know how accurate the implementations are, we are featuring a set of benchmarks, very general benchmarks solving the Boussinesq equation, for example, or a problem, but also benchmarks for the two-phase flow or three-phase flow, as well as for context and constitutive models. As I said, the NUMGEO is primarily a text-based program. So if you're interested in the features, you want to know, well, how is such a command? What does it do? How is it defined? We have an extensive documentation of all the different aspects and commands. So for example, if you want to know how to define a material, you can go to the material card, and you see already, okay, a material has a lot of options like the density, a mechanical model, which is a stress-strain relation. And then if you want to know, for example, well, okay, how do I have to apply Seniscent parameters? Then you can click on the Seniscent 2, and you will get a command that is ready to copy, and you can paste it wherever you want, and you have a detailed description of each of the parameters, and also some optional flags or parameters that you can use. So it's quite extensive. We are currently also building the theory manual. So it gives you information about, for example, how we are solving the system of equations. So we're using Newton-Raphel method, and it also gives details on the convergence criteria. So you can read in detail what we are doing in our code. And then I think interesting for a lot of people is also the graphical user interface, because most of us, we don't really want to write a text file to get a simulation running. So the graphical user phase has its own documentation. We're currently building that. There are already quite some installation instructions. You can easily follow them. And the manual gives you also some details about the data tree. All the different options that you have are detailed here. And the tutorial section is currently quite a bit empty. So we are building that, but there is more to come in the next couple of weeks. So with that, I would, if there are, or maybe we can have just a quick break, at least if there are some questions, before I would start with the hands-on of quite a simple problem. Are there any questions so far?
Sí, ¿qué tal? ¿Hay alguna consulta? Si desean hacer una consulta al profesor Jan, pueden hacerla en español y se la traduzco directamente, o pueden escribirla en el chat para que podamos comunicársela.
Okay, so if they are not, I would continue. If that's fine for you, there is maybe one.
Sí, sí, ya podemos seguir y mejor dejamos las consultas para después. Yeah, we can continue.
We can continue. Okay, fine. So the example that we prepared for today is a rather simple one. The reason for that is just to, in terms of giving an introduction, it's easier to start with a simple geometry, a simple problem, and also I can run it quite quickly so that we don't have to wait for the results. So the problem that we want to look at today is a very simple strip footing problem. So we have a strip footing foundation that is resting on top of a soil. In our case, we will consider a sand. So the sand, the domain has just 10 meters on 10 meters, 10 meter wide and 10 meter height. And then we have a foundation has a width of 1 meter and the height of 0.5 meters. Now we will load the foundation with an external load, so a surcharge of 200 kilopascal. So that will be the problem that we will simulate. For the soil, we will assume the soil to be ideally dry, meaning we have no water and it's completely dry. So it will have a dry density of 2 tons per cubic meter, and we will use the semi-sand model, so quite an advanced elastoplastic model. We use the parameters of Nevada sand, but this is just a choice that we did. You could use obviously every other parameters of sand that you would like to use. Now for the foundation, it has the same density. I'm sorry, I'm missing here the density, but we used for simplicity the same density as for the dry soil, which is obviously not that realistic, but compared to the 200 kilopascal external force, the self weight of the foundation is not that relevant in the present case. The foundation will be model linear elastic with a Young's modulus of 25 gigapascal and Poisson ratio of 0.2. Now, between the foundation and the soil in the interface, we will consider a frictional contact where we set the friction coefficient to 2/3 of the friction angle phi, so approximately 0.36 in our case. So these are the some of the parameters of that model. In terms of the stages that we will consider, we will start from an initial state where we have only the geostatic stress state. So we have the soil, which is underneath, which has a stress distribution due to its self-weight, linearly distributed of 200 kPa at the base, which is just 2 times or 2 for the density, times 10 approximating the gravity, and then times the 10 meters that we have in height. Now, what we will add is we will add a small artificial surcharge of 1 kilopascal. So we will add here a small additional load on top of our soil of 1 kilopascal. And we use that 1 kilopascal load only to stabilize a bit the Sunny Sand model. So these advanced soil models could be Sunny Sand, it could be a hyperplastic model. They perform very, very poorly if the stress goes very close to 0. So we always need a stress that is larger than 0. And obviously, if our integration points are very close to the top, the stress level is quite low, and then we might face a bit of numerical issues or problems. So that's why we add 1 kilopascal of external additional load on top of the soil. Then in terms of the loading, we will add the load that is here shown in this with this blue arrows, so a load of 200 kPa. And we will apply that load gradually, so monotonically increasing in a way that at the beginning, let me see, it's our load is 0. And at the end of the step, we are reaching a value of 200 kPa, acting downwards, so pushing on the foundation. And for this linear increase, we will use the time or a physical time of 1 second, but this time has not really a physical meaning since we will perform a static simulation. So this time can rather be seen like percentage of loading. Now, the steps that we will now follow during that tutorial will be that we will first create the geometry. So we will create the soil and the foundation. We will then assign the element types, which will govern the physics that we are looking at. So this will be very simple here since we're looking at a dry soil. Then in the third step, we will create the material definitions. So the Sunny Sand model and the elastic foundation, and we will assign it then to the different parts of the model. We then need in the fourth step to define the contact between the foundation and the soil, specify the initial conditions, meaning that we have a geostatic stress distribution like this one. And we also need to assign some state variables for the Sunny Sand model. So most advanced constitutive models of soils, they need some additional state variables. They all depend on stress, so we don't have to specify that, especially because we can use that already from the geostatic stress. But the Sunny Sand model also needs information about the void ratio. So we also will specify that one. And then we will define the loading stages. We will have 2 stages. The first stage will be the geostatic equilibrium step. And then in the second, from that equilibrium, we will start our loading step. After having done all that, we will generate a mesh, run the simulation, and look at the results using ParaView. So that's the outline for the next part of this introductory lecture or presentation. Okay, with that, I would open GID. So we will do everything in GID. And I have created for myself a small cheat sheet, let's say, where I've listed some of the parameters that I will need in a minute to create the model. So I hope that you can see well the drawing canvas and everything. Okay, good. So there are several ways in GID to create a geometry. So that will be our first part. So the first step is creating a geometry. To create a geometry, in our case, it's a very simple geometry. Remember, we have that rectangular shaped soil and above of that, the rectangular shaped foundation. So I will start using that by creating the lines of our soil. And there are different types of doing it. So I could press now and draw the lines and change the dimensions later, or I could immediately insert the points in that small command window at the base. And this is what I at least like to do. And the first point, I will place that right in the center of our coordinate system. So at x equals 0 and y equals 0. And then, as we said, we have a 10-meter wide foundation. And it's also 10 meters in height. So the next coordinate would be 10, 10. And then obviously we will close now this rectangle, meaning that the next coordinate will be in the x direction 0, and in the y direction will be again 10, and then we can close it. So GID will automatically ask you whether you want to join these 2 points, and we want to do that. So we want to close this geometry. And what you will notice now is that you don't have really a face, so you only have lines. In order to have a 2D simulation, what we need to do is we need to create a surface from these lines. So we can do that using the surface, create surface tool. We select all the lines that we want to use to build that surface, and then we press escape. Escape in GID is confirm. So we confirm the selection, and we have created a surface. Now, what took me a while to get used to is that surfaces are highlighted with these purple rectangles or lines. But you can also look at it in a different way if you want. So you can go in with the right click, render, and then you can use the flat render, and then you can see that you have now created a surface. GID works in layers, and this layer, we will call that layer soil, since this will be our soil. The naming that or the names that you use here are completely arbitrary. So you could also use sand or whatever you want to use. It has not a real meaning in terms of the simulation later, but it just makes life easier to give the different parts of your model a proper name. So what I want to do now is I want to create the foundation. And for that, I will create first a new layer. There is a shortcut for that. It's a small button here. And then you can see that you have a new layer and you can give it a name immediately. I will now name it foundation. And what you can do now is you can work, let's say, in both layers simultaneously. But what I want to do is I want to close the layer of the soil. So you see it changed the color a bit. It is now not accessible anymore. I see that it's there, but I can't access it. And now I will create the foundation. To create the foundation, as I said, the foundation has a width of 1 meter and the height of 0.5 meters. So I could create the foundation somewhere in my drawing canvas and later move it, translate it then to be just on top of the soil. But since this is such an easy geometry, I will immediately place it in the right position. Again, I will enter the coordinates down here in my command window. So the x, so the first point of the foundation will be again at x0, but at the y coordinate of 10, so at the top of our soil layer. So you can see the first point is now created here. And now I will create the second point, which is now at x of 1, and again a y of 10, which leads us now to the line here. And then I will create this 2 next points. We stay at the x of 1 meter, and now we are at a total height of 10.5 because our foundation is 0.5 meters high. And from there we go again to the left border. So 0 in x and 10.5 in y. And then we close our geometry. And just as for the soil, we will create the surface from that. And you see now we have created a second surface. I can unlock again our soil, and we now have the complete geometry of the soil and the foundation. Now at this part, I want to load now all NUMGEO features. So for that, I go to Data, Problem Type, and I select NUMGEO. Then it takes 10 to 15 seconds to load everything up. And you see now that there's a data tree that is specifically tailored for NUMGEO. So if we just take a look back at this list, so we have created now the geometry. The next step will now be to assign the element types and to create and assign material definitions. So these are the next two steps that we will perform. So in terms of the element types, as I said, they will govern the equations dictating the physics of our simulation. So for that, we go to assign element type and again use assign element type. So this is used for continuum elements. There's a second one for trusses and beam elements, but we will stick purely to continuum elements today. So we go to assign element type. We can double click on that. And then we have to select the formulation that we want to use. And as I said here, we will make our life very easy. So we take a single phase solid simulation or equations. We use full integration, and now we have to assign it to our parts of the model. So for that, we select surface, and we can now use the button select. And can select the geometrical entities in our drawing canvas. So everything that is red is selected. If we are happy with our selection, we again confirm using escape. And then we have the option to rename it, what I will do. So I will name that now all, because I have gathered the soil and the foundation, let's say, in one group. So I give it a name all, and I confirm with OK. So if we now go on the right side, so you see layers, but right from the layers, there's the groups. And you can see that automatically a group all was created. You can toggle the visibility on and off to see what is that group all. And you can see all is just everything that we have in our drawing canvas at this time. You can also see in the assign element type that now we have a group all. And you can see, okay, we have selected the formulation single phase solid, integration full. So you have access to your decisions here. Now, from there on, we have to define the materials. So the first material that I want to define is concrete. So I take again the material one. I will rename it to something meaningful, concrete. As I said, we have a single phase simulation, no water to take into account. For the density, so we will change the density. We will put it to 2.0 as specified in the tutorial, and then we will select a linear elastic material model. So we select linear elasticity, and then we have to specify the Young's modulus. In our case, it was 25 gigapascal and a Poisson ratio of 0.2. And then we confirm with OK, and that's all we have to do for the concrete. Now we create a new material. So to create a new material, the second one, we go right click on materials, create new material, and then we can choose a name. In this case, I will take sand. Again, you can see that usually it takes already the information from the previous defined materials. So the density is already correct, but we need to change the stress-strain relation. To do so, we can just now select the semi-sand model. That's the one that we want to use. And you can see that immediately, dynamically, the parameters will appear that are appropriate for the semi-sand model. So I want to open it in a different window. It makes it easier for me to enter the parameters. And this will just be a bit of a boring copy and paste. So we have to specify the parameters for the critical state, which is the void ratio at the critical state and zero pressure. Then we have the lambda and xi, which determine how this void ratio decreases with increasing pressure. Then we have to specify the friction angle related parameters like MC and ME. We then give the parameter for M, which is the opening of the cone for the yield surface. Then the parameters G0 and the Poisson ratio. And then the other parameters, which are pure fitting parameters, determining the material behavior under various different loading conditions. So I will just copy them in there. And then we are set, right? So having introduced all the parameters again, we can apply or confirm using OK, and then we have all the parameters specified. So that's all. With these few steps, we have created now the two materials that we need for that simulation. But now these materials, let's say they are unused. They have been created, but they are not assigned to any part of the model. Now to assign these parameters, we use the assign material tool. So we open it up and go to assign material. And now we first need to select the material that we want to assign. So let's select the concrete, and you can see only the materials are shown that we have created previously. So we choose concrete. Again, we select the surface. So now we cannot choose all, because then we would assign the concrete to all our domain, which we don't want to, obviously. We go again to select, and now we select only the foundation. We confirm with escape, and we can now create a new group. I name it foundation, and you see that the foundation is now created here on the right-hand side in the groups. And you can see it also here under the assign material. You have it here with the material name that you chose. Now we want to assign a new one. So we need to select the sand. Again, the surface select. We select our sand. So for example, you could also just use the automatic assigned name. We will do that now, and you see that it appears here on the right-hand side. But obviously that is not very elegant name because it doesn't tell us anything about the modeling, but we can rename that at any time. So we can rename that and call it soil. And what you see is that automatically the assigned or assignment is updated as well. So if you change something in the group names, it will also be changed in the assignment. Now, having now created the materials and assigned them, the next step, or let's have a look at the next steps. So the next step is define the contact between the foundation and the soil, and then also assign the initial conditions. So these will be our next two steps. So to do so, the first thing will be that we open contacts and we enable contacts. So we go to contacts required and we toggle that to yes. And then you have more options that will appear. So at first, we will have to select the master surface. Usually, we use for that the surface of the structure of the material with the higher stiffness. Now, in order to easily select the base of the foundation, what I would do again is I would just lock the soil layer, which gives me only access to geometry entities of the foundation. So I can double click on the master surface. I select lines. And you see, I could also select already defined groups, but we don't have a group that matches our requirements. So we go to select and we select now the foundation base. And I will name it foundation base. I enter with OK. And then I will unlock again our soil. Then I will select a slave surface. Again, I select lines. I select now the entire top surface of our soil. So there is no need to create another, let's say, intersection here so that we have only a small part of the soil. We can create or just use the entire top surface. I confirm. And then I will name that soil top. So with that, we have specified which areas will be in contact with each other, but we have not specified the behavior. So for the normal contact behavior, we'll use a penalty approach, and we will just use the standard, the default settings. But for the tangential contact, what we do now is we change the friction coefficient. And we said that we use 2/3 of the friction angle phi, which is the friction coefficient of 0.36. We can do so by clicking just here, 0.36. I think that I mistyped something. Let's see, 0.36. Yeah, so I think I did a double dot. So now we entered the 0.36. And with that, we have defined everything required for the contact. So we have chosen the master surface, the slave surface, and then defined the properties for the contact. And that's it so far. What we will do now is we will create an amplitude. We will use that amplitude later. We use the amplitude to define the monotonic increase in the load. And for that, what we do is we use a ramp, right? So maybe we can go back on the slide. So we want later to increase the loading starting from 0, going up to 200 kPa. So we need to have an amplitude that starts at 0 and takes a value of 1, that's one option, or the value of 200 after 1 second. I will tell a bit more about that later in the step stage. So what we will do now is we will create an amplitude starting from time 0, having the value 0, up to time 1, having the value of 1. So we can just use the default values here and confirm. So the next step now is to define the initial conditions. Like in all our geotechnical simulations, we have initial stress that we have to account for. So for this, we can open the initial stress option and double click on the initial stress. And then we can enter different types of distributions. In our case, we want to have a geostatic distribution. The geostatic distribution tells us that we have a linear increase of the stress with the depth, and we will have to specify the ordinates. So our first vertical coordinate, or the height, let's say the first height of our model where we want to specify the stress, is exactly at 10 meters. So the top surface of the soil. And usually we would say that the stress is 0, but as I said, we will apply a small additional load of 1 kPa. So the stress at the surface will be -1 kPa. So we are working here in the coordinate system, right? So you see that y is pointing upwards. So our stress in our case is negative, our compression stress is in this case negative. So if we go to our second height, which is 0, which is at the base of the soil, and in this case, the stress would be -200, since we have a density of 2. But we have also this 1 kPa of surcharge, so we have to prescribe -201. And this is the vertical stress. To have the horizontal components, you can specify different K0 conditions. In our case, we will just use the K0 of 0.5. Again, you have to select the entity to which you want to apply that. We don't have to select it here from the viewport. We can just use one of the already defined groups. And in this case, we use the soil group because we want to apply that initial stress to the soil. And then we can confirm with OK. Now, as I said, in addition to the initial stress, what we need is initial void rate in the state variables. State variables especially used for the advanced constitutive models. So again, we can double click here. Here we will assign a constant value of void ratio for the entire model, for the entire sand. So we can use the default option. And since different constitutive models have different state variables, they are not consistent across all these different models. We are now in charge of choosing the right one. And so the way that we decided to go for here is that we write the name of the state variables. This gives us the maximum flexibility that we have for all these different advanced constitutive models. And in our case, the void ratio or the name to assign a void ratio is just void underscore ratio, and then we assign a value to it. In our case, we will use 0.7. So it is a rather loose soil close to the critical state. And then again, we have to select the entity to which we want to apply it. And for this case, we again want to apply to the soil. There is no requirement to give any additional state variables to the foundation since it uses linear elasticity. So there is no additional information required. So only the soil needs that treatment. So we confirm again and close the initial conditions. So now from that, if we go back to that, to our slide, we can see that now we have to define the loading stages. As I said, we will start with the geostatic equilibrium step, and then we will apply the loading. So we have two steps: equilibrium, initial step, and then the loading step. And after that, we will generate the mesh and run the simulation. So for the steps or loading phases, so for the Plaxis users, you would call that a phase, a calculation phase. In our case, it's a calculation step. So we follow the naming conventions of Abacus. We create a new step, and you can see one is already there per default. And the first thing that we do is we choose a type of the analysis. And in our case, we want to switch that from static to geostatic. So geostatic analysis is a special procedure to find the equilibrium for the initial state. What else do we have to do? Well, we have to define our boundary conditions, starting with the Dirichlet boundary conditions. And in this case, we want to constrain the displacements. So we go to Dirichlet boundary conditions and use or choose solid displacement. We double click, and then we can choose different types. For example, we could use it could be linear distribution, or it could be a moving hydrostatic boundary condition. But in our case, we want to fix something, so we only want to prescribe a scalar value. We want to prescribe displacements, so there is no velocity acceleration. In our case, it's a static simulation, so only displacements are of interest. And then we want to fix it now in the x direction. Y should be free. So I want first target our lateral boundaries, and I will select line. And now again, I have to select the geometry from our viewport. I will do so. I select the left line of the soil, the right line of the soil, and the left line of the foundation. So these should all be fixed in x direction, but free to move in y direction. So I confirm again with escape, and then I will just call that BCX for boundary condition in x direction. And I apply with OK. And then I will do the same for the bottom of our model. So again, I will use displacement. This time I will leave the horizontal displacement free, so it can move at the base in horizontal direction, and I will only fix the y direction. Again, I select lines. I will select the base of our model, and I will call it BCY for boundary condition in y direction. So that's the Dirichlet boundary conditions. If you want to have a look, then we can see the different entities to which the boundary conditions have been applied. And then we can move on to loading. So we will define the loads. So the first load is obviously gravity. We always have gravity in our simulations. So we double click on gravity, and we will simplify the gravity for this example as 10. Obviously, so 9.81 would be maybe better, but it makes life a bit easier to just use 10, and for the problem at hand, it should be good enough. We want this gravity to act immediately. So there's no ramping up of gravity or something. It is there from the start till the end of our step. So we use the loading ramp instant. And then we will apply it to all our entities. So to the foundation and the soil, all of them obviously have gravity acting on them. So we confirm, we have now defined the gravity. And now we have to find that one kPa additional surcharge that I was talking about, right? So we add a pressure of -1 kPa. It also should act immediately, so right from the start of the simulation, and we will add that on the soil top surface, and we will confirm with OK, and then we can have a look, and we see that there is the loading acting on top of our foundation, so it seems to be working just fine. So now we have defined the loading, and now we want to specify the outputs. So we want to see some results later, and we need to specify what we want to look at. So first we want to specify what information we want to have at the nodes. So for that we want to have obviously the solid displacement, but we can also look at the stress at the nodes. So if you specify stress at nodes, what we will do is we will extrapolate the stresses at the nodes. They are calculated in integration points, so inside an element, but we will extrapolate them to the nodes. We will specify that we want to have that information for all our entities in the model and confirm with OK. And then we can do the same for element output. And there again, we can specify stress. Maybe we are also interested in the strain. And again, we want to have that information for all the entities. So we select all and press OK. So that is our first step, the initial step. From there, we now need to add the second loading step. So what we do is now we copy that step and we choose copy with assigned groups. And then we have step number 2. So why did I do that? Well, the reason is that everything that I've defined before is now defined as well. So I do not have to redefine boundary conditions. They are now inherited from the step before. So the loading and the directly conditions are already prescribed, and we do not have to do that step once again. But what we will do is we will now change the type of analysis. So now we want to perform a static simulation. So we change that. And what we also want to do, we don't have to actually, but just to give you a bit more insight, what you could change is we want to change the time integration. What you can do is you can specify an initial time step. So the step with which this, or the times increment with which this step starts. And then from there on, we use an adaptive time incrementation. So if the convergence rate is very good, we allow the solver to increase the time step, so to accelerate the simulation, but we can also cap that one, right? So we specify a maximum time step. In this case, it is 0.1 seconds. And if the convergence rate is very bad, the solver will try to reduce the time step to capture maybe better the nonlinearities, but also for that, we can define a minimum time step. And once the total time of a step reaches 1 second, the step is terminated and the simulation is finished. So here we will now choose just a lower initial time step of 0.005 seconds. So now with that, we have done all the required steps. We have assigned the element types, defined materials, assigned then the material, defined contact interaction between the foundation and the soil, describe the initial conditions, and then also define the loading steps with step number 1 and step number 2. So the only thing that we need to do now is we need to mesh our model. Before that, I will just quickly save the model once, and then we can go to mesh. And in our case, the geometry is very simple. So we can use, let's say, the highest quality elements that we have, rectangular elements in our case, what we want in a structured mesh. So in GID, we can easily create a structured mesh. We can go to mesh structured surface. And now we want to define, or we use the option to define the number of divisions. That means we say how many nodes we have on the lines of the surface. You could also prescribe a size if you want. You could also leave the mesh completely free to GID to generate. So there are a lot of options. I'm making it maybe a bit more complicated than necessary now, but just to show you the different features that you could use. So in this case, we will select now our soil domain. And now we can specify how many elements we want to have on each of these sides. And we will go with 40 on both vertical and also horizontal lines. And then we again confirm with escape. And then we can close. And we do the same for the foundation. So mesh, structured, surface, assign number of divisions. I select now the foundation. So in this case, I want to have 10 elements for the horizontal one, this one. And then I want to have 3 elements in the height. So there is no need to have the same number of elements for all the sides. And then I can close. So now we can define also the element type. I want not to have triangular, but I want to have quadrilateral elements. I select all geometries, and again, I confirm. And now I can create or generate the mesh. So it takes a second, and then we can go to view mesh. And now you can see the mesh that was created. So you can see that we have a regular pattern for the soil, although we already know that, let's say, the region or area of interest will be the area around the foundation. So we would like to concentrate the elements in that area. And we can do so quite easily. So we can go to mesh structured lines, and then we can select concentrate elements. And with that, we can select the 2 horizontal lines. And it is hard to see now, but there is a small error. Maybe you can see it if I zoom out. So I already contacted GID so that they should draw these arrow largest, but the arrow is pointing from the left to the right. And that is important when we want to assign the weights, because now we have to increase the start weight. And so we will have more elements below the foundation and less elements on the right-hand side near the boundary. We can confirm, and then we select the 2 vertical lines, and we do just the same, but this time the arrows, they're pointing from the bottom to the top. So what we need to do now is we take the end weight higher to have a concentration of elements right below the foundation. And then we press OK, and we regenerate now the mesh. So we go mesh, generate mesh, OK. And then we can view the mesh, and you see now that we have a concentration of elements close to the foundation. Now, what you also see, if I zoom in a bit more, is that we have not a conforming mesh below the foundation. So you would need a conforming mesh when you're using node-to-node contact, but for the mortar method, we don't have that constraint. So we are fine with using it in a way like it is shown here. So with that, we now need only to generate the NUMGEO files. So we go to NUMGEO, generate NUMGEO files, and they are already generated. And you can find these files if you go to the place where you stored the, or where you saved the model. So I saved the model in our workshop directory simulation, and there is named strip footing. So this is a GID model. If I enter that, I find a lot of files. So these files here, they are all internal to GID. The 2 files that were created are the ones here. And these are the text files that will be used by NUMGEO to perform the calculation. So we have one calculation file. If you double click on it, you can see that is a text file. I will make the text a bit bigger. I hope that you can read it. And what you see is that you find the material definitions that we had. So we have a material that is called concrete, which has one phase, which uses a stress-strain relation, so mechanical model that is called linear elasticity, with a Young's modulus of 25 gigapascal and a Boltzmann ratio of 0.2 and a density of 2.0. So you see that although it is a text-based file, it is not that difficult to read actually. But of course, it is easier and more comfortable to create such a file using the graphical user interface. And you will find all the information here. So you find the material definition, you find the contact definition, and also the steps that, or the calculation phases. Now you also see that not all the information is stored in one file, but we can also distribute the information to different files and then gather them in one parent or one main file. And in our case, we excluded the mesh. We do that for an obvious reason, because especially if you have a bigger problem, such a mesh file is very large. You have the node definition, the elements, and so on. And usually you don't want to look at that, right? So the more important or interesting things are the calculation stages, right? So by clicking on NUMGEO, generate NUMGEO files, these two files have been created. Now to run the simulation, what you do is you go to calculate and then press calculate. Now, before we want to do that, I want to change one thing, and that is I would like to use not only one CPU, but I want to perform it multi-threaded. So I will choose 2 CPUs to accelerate the simulation a bit. And then I go to calculate and press calculate. Now, if you go to calculate view process info, there will be a window which gives you information about the simulation process. So the first step is already finished. You can see that's the geostatic step. And the second step was running. And it is finished now, right? So it took now approximately 15 seconds. So it's a very simple example here, so that we don't have to wait that long. But you can see that especially for more complex simulations, you will have a clear look on the process of the simulation in that window. Now, if we look now at the directory here, we see that a lot of more files have been created. There is a file with an ending PVD, that's the preview file. So here are all the outputs stored. That's what we want to open if we want to look at the results. But there are also different files like a message file. So I will make that window here bigger. Just a minute, I have to, yeah. We'll make it bigger. So this file is usually not really interesting for most people, but it gives you detailed information about the convergence behavior, right? So for each iteration, you will have information about how accurate your simulation or your result is, and how the convergence criteria are met or not. Right? So this is one file that is being created. There is another one, a log file. That's one that is created right at the beginning. And this file gives you a bit more information about what is currently being done and summarizes important parts of the model. So your model has a total of 5,000 nodes, 1,600 elements, and so on. Right? So we have different files with a different meaning and information to it. But I think the most interesting one is obviously now the output. So we can double click here, automatically ParaView will open. And you can see now the model here displayed here. So we can toggle on the mesh. So we can choose surface with edges. And then we also can see the mesh. And from there, we have access to all the different outputs. We can look, for example, at the displacement at different time steps. So in this case, we are right at the beginning. So at the end of our initial step, so at the end of the geostatic step, we see that we have not a perfect initial equilibrium. This is because we had the self-weight of the foundation that is already acting due to the gravity, but that we did not consider when we prescribed the initial stress. So we did some inconsistency, if you want, but it was not a big problem. We have, let's say here, 2 millimeters of deformation because of the self-weight of the foundation. So there's no additional loading here, just the self-weight. So if you want to know now, for example, how this displacement grows with time, we can move through the different time steps, bit by bit, for example. You see that the displacements, they will grow. Or what we can also do is we can look at the video. Now, maybe okay, I'm very sorry. I forgot one point. So I was just wondering why nothing is happening here. and I forgot something, and that is I forgot the external loading. So I'm sorry for that, but this is a quick fix that we can do. We just, in the second step, add another loading. Right, so we go to pressure, double click on pressure, and now we want to add 200 kilopascal negative. And what we want to do now is we want to choose amplitude. And then for the set, we want to use soil top. And then we choose the amplitude number 1. So that will lead to the ramp up of the loading. So if I now recreate the NUMGEO files and I press calculate again. So I'm very sorry about that. I was talking, and by that I forgot to add the additional load, but it should be done in a minute. So you see the process is now maybe a bit slower since the solver has to do a bit more, but it's still in a reasonable time or speed for this type of tutorial that we have here. So we will be done in a minute. Yeah, so now it took a little longer, 30 seconds. Now what we can do is we can stay in that window. We just reload the files. And what we will see now is that we have in fact some loading. And now I think I did. Okay, so now you got me. I did another error. And this is, I assigned it to the entire top surface. I mean, we can look at it, but that's why we have a big settlement for the entire foundation. So if you want to look what is happening, you can see it. I applied the load now to the top surface, but this is obviously not what we wanted to do. Again, we can just unassign the group and apply a new one. So again, minus 200. We use an amplitude 1, select the line, and now we apply to the top surface. So we select the top of our foundation and say foundation top, press OK, and then we generate our NUMGEO files and we redo the calculation. And I hope that I did not forget something else now, but at least it shows that you can change certain parts of the model quite easily using the interface. So now let's see if it works better. You can also look at the results during the calculation, so you can update that in an ongoing way. And now it looks much better, much more like what we expect. We have the settlement biggest below the foundation, and yeah, looks much better. So let's see how the process is. It's nearly done. Okay, so now it's done. And now we can reload the results. And yeah, now we see what we would have expected. We have a settlement beneath our foundation. There it's biggest, and then the settlement becomes less and less with ongoing or with increasing distance to the foundation. So we can look at displacements in different directions, right? Displacement is a vector field. So we can look, for example, only at the Y component, so only settlements. You could also look at stresses. If we are interested, let's say, in the vertical stress, then we would see that we have a stress concentration below the foundation, which is especially due to the contact zone. And we could look also at strains, for example. So you see now also the difference between nodal output and element output. In the element output, you have a non-smooth field, and you get one constant value for each element in this case. And there is no extrapolation done. In turn, you could also look at let's say at more at cuts of your model, for example, right? So if you're interested in the stress distribution below the foundation, we could create such a plot we could go to filters, alphabetical, and then, for example, choose plot over line, then you see that there is a line that you can draw in your model. So you can either drag and drop it with your mouse, or you can specify start and end value. So, for example, if you want to be quite close to the left boundary, so maybe 5 centimeters from the boundary condition, and then we are interested in, let's say, starting at the top, just below the foundation, and then going right to the bottom, and obviously z coordinate is 0, so we can apply here. And then you get all types of plots on the right-hand side. We have first now to select what we are interested in. So in our case, for example, I would like to look at the vertical stress on the x-axis. So I have to select the value of the x-axis. I can do that. So I select the stress y, which is the vertical direction. And then I'm selecting the arc length. The arc length is the distance along the path. And to see if we're looking at the right thing, then we can go to the beginning of the simulation where we have our initial stress field. Now you see that it's -10 at the base, or at the bottom of the plot. This means that the bottom of the plot is now just below our foundation. So we can switch that easily so that it's maybe easier to see. So now we switch our path. We start at the top and go to the base. So at the top, we have -10 kPa, which is just below the foundation, self-weight of the foundation. And then we increase until 202 kPa at the base of our model. And now if we're interested in how with ongoing loading this stress changes, you can look at a small animation, for example, where you see how the stress increases also at the top. You see that these smaller oscillations there, which is because ParaView samples along this line, and it's rather an extrapolation feature, let's say, of NUMGEO. It's not the stresses of ParaView. It's not really the stresses that are fluctuating. So you have all type of different options to look at results. You can create these contour plots, animations. You can create cuts, and you can also have point-wise values. So you could select a node and then look on how stresses or displacements will evolve during time, for example. Yeah, so with that, I'm at the end actually of my part of that introduction. I think maybe there are now some questions. Not sure. Let's see there in the chat maybe. Okay, Patrick has already answered a lot of these questions. But are there any questions to which I should answer here, or anything else you would like to see?
Hi, Jen. I have one question, or can you hear me?
Yes, I can hear you.
Okay, perfect. About your optimization parameter model, when it's going to be released to the public? Is it still in development, right?
Yes. So the optimization tool, you mean the automatic calibration tool?
Yeah, that's right.
Yeah. So I have currently 2 PhD students who are close to, or they will submit end of this year, beginning of next year. Then they will have their defense, and we agreed on to wait until they have finalized their PhD, and then we will roll out the tool. It's just to make sure, let's say, that they have enough time to publish their results.
Okay, perfect. It uses some kind of artificial intelligence to calibrate the parameters, or is it just...
Yeah, so what we're using is basically machine learning. So I wouldn't go that far to say artificial intelligence, because it's mainly optimization. Right? So you're using meta-heuristic optimization approaches. so it's rather machine learning. We are currently building a big database. So for different types of soils, different grain size distributions, and so on. And then we hope that we can maybe train something to at least give a first estimate, right? So let's say you have limited amount of information from field data, you have a grain size distribution, maybe you also have 1 or 2 tests that you could estimate, at least for a first prediction, rough prediction. You can estimate a set of parameters and then maybe identify areas where you sample more and then have a proper calibration. So that would be the goal, let's say, at the end. But currently it's pure optimization. So you feed in experimental data and you get out a calibrated model.
Perfect. And one more question, please, if I may. Is there a problem with NUMGEO when facing brilliance in some materials related to the mesh size?
How exactly do you mean that? So you mean, let's say, so for example, wave propagations, right? So you have, let's say, certain requirements for time increment size and nodal distance or element size. Is that what you're aiming for, or?
I'm thinking more like some softwares like Plaxis have some issues when we try to lower the mesh size with very little mesh lengths. We have like mesh dependency on the results with yeah.
So
you understand what I mean?
Yeah, so usually we don't see that. There is a bug connected to it because it depends a bit on the constitutive model that you're using, for example, right? I mean, we have in geotechnics always the issue of localization. If you're going to the critical state, localization is an issue, and mesh refinement not always helps, right? But this is rather a problem of, let's say, the constitutive models at the end, if you go there. But other than that, usually if you refine the mesh more and more, you're getting more accurate results, right? I mean, obviously, if you refine the mesh very much and you go with that to the surface, then your integration points are going in a very, very low stress state. And most of our soil models behave very badly in these type of stress states. Then you would also have problems in NUMGEO. But again, it's a matter of, are we in an admissible stress state or not? But other than that, we have not encountered, let's say, issues with mesh refinement, right? At least in the convergence studies that we have performed so far.
Okay, perfect, Jan, thanks. And one last question is, when facing large deformations, such as in dynamic problems, as you just told us about, NUMGEO has an option to rezone or rebuild the mesh to take those large deformations into account to avoid mesh problems.
So what you can do currently is we have the option for nonlinear geometries. Nonlinear geometries is the same as Plaxis calls updated mesh. But Plaxis is not updating a mesh at all, right? So this is just their name for nonlinear geometries. So taking into account rotational components of the deformation and considering that. So we have that option to include nonlinear geometries in terms of even larger deformations, right? So if you're in an area where the mesh quality deteriorates because the elements are severely distorted, we have currently, well, we are building currently a particle finite element addition to our code. So it is built in NUMGEO. We are currently building it. I think it will take a year or two until we roll it out, right? So until it is robust enough to be used in practice. But we are working on that one, and there you would have automatic remeshing, right? So what you could do is you could just start a simulation, and then the mesh will automatically be updated in order to have a good mesh quality throughout the entire simulation, even for large deformation like runout simulations or dynamic compaction or things like that. So what you could currently do is, obviously you could always cut your simulation in smaller parts and then perform some sorts of mapping of the states, right? So you could model until a certain deformation occurs, and then you could build that model, the geometry, load that in GID again, remesh it, and then start the simulation from that stage on, because you can read in initial states, and you could read in old states, for example, but that is a very manual approach. And yeah, so for an automatic approach, we are currently working on that in a project, and I guess that it will be ready 1.5 years or 2.
Thank you very much. Si alguien más tiene una consulta adicional, puede prender el micro y lo traducimos. Sí, adelante, Edwin.
Gracias, Juanjo. Jan, I have a question. I want to know if you have think or you're developing another constitutive models a bit more common, like Hardening Soil and or North Sand.
So we can implement more models. That's generally possible. We also develop our own constitutive models, and obviously we also implement them. In terms, for example, North Sand model. So the easiest for us would be if someone provides us with a model and we interface it, or someone uses the interface, the public interface that we have, to add a constitutive model and add it on their own, right? So that would be obviously also an option to do so. For us, we are not really using North Sand. So we would, to be honest, North Sand would not be on the top of our priority list if there's not a good reason to implement it. We are doing such implementations when we have time. So we have done it in the past. And we can also do it again. It's rather versatile, but it is the easiest, obviously, if there is a well-written implementation that we can use and interface. That would be the easiest way for us, and the quickest way for us to interface it. I'm not sure about the North Sand model. I know that there are dynamic linked libraries for Plaxis, for example. If it is written in Fortran, or if it is written even in C++, I think we could, and we would have access to code, we could interface that also to NUMGEO, yeah.
Okay, also a couple more questions. And how about Hardening Soil small? Have you thought about implementing that model?
Yeah, so we don't have currently an implementation of Hardening Soil and Hardening Soil Small. We started implementing it, but it will take us some more time. Hardening Soil model is, I think you all are aware of it. It's the most widely used model, but at the same time, no one is sharing any implementation, and all programs give different results. So there seems to be different ways of implementing that model, and well, we are right in the middle, and we have to, at the end, to decide, well, which one we want to match and which not. And yeah, yeah.
Yes, of course, because I think that would be a great benchmarking with other software, so that people can trust in this model. Well, like we can see, I think that it is a really good one. Also, my last question would be about the 3D dimensional models. I know you have some experience about what was the biggest model that you have ever implemented? Can you tell us a bit more about that?
Yeah. So actually, so for myself, the biggest model that I've implemented was actually in 2D because I was working for mining industry. So for RWE power. And so I had to simulate slopes of their open cast mines that were then later filled with water to create residual lakes. And these models, they are 8 kilometers in width and 1 kilometer in height. And the slope is 800 meters and it's a stepped slope. And we had to use, so it's saturated soil and the earthquake loading. So we had to use sunny sand, hyperplasticity. So let's say we used the very advanced constitutive models. And we had, so it were quite a few million degrees of freedom that we had with these nonlinear models in dynamic simulations, so rather big. So that's the biggest that I have simulated, but this is 2D. But in terms of the scale, it was very big. And it went well, right? So such a simulation earthquake length of 20 seconds, depending on the distance of the epicenter, was about 20 seconds the longest. Took about 2 to 3 days on a standard workstation. So it was okay. In terms of 3D, we are mostly focusing on, or we have done a lot in terms of pile raft foundations and also monopiles, right? And foundations for wind turbines. And there also usually we have quite a few 10,000s of 3D elements in these cases. So.
I see. I see. Thank you very much. And well, I was asking because I can sense that the industry, at least the mining industry, is tending to start to making some 3D models. So it would be great if you can consider that in the future. Thank you very much.
Adelante, Juan.
Jan, is it possible to have a demonstration of in NUMGEO of slip surface propagation for bearing capacity?
Yeah, so it would take us some time to do that now. Also, slope stability. So what I would rather point to is, so what I thought is that we could do that maybe in a second meeting altogether, have, for example, a factor of safety determination. But you can have, if you're eager to see it or to do it on yourself, you can also go to tutorials, for example. And if you go down to slope stability simulations, there is, for example, an example of a slope stability of simulation determination of factor of safety. I will upload in a couple of weeks a few more examples on slope stability, also with retaining structures, because we did a big comparison with the German geotechnical society, the Numéricos group from there, where I'm part of. We compared different software packages for different type of strength reduction problems on dry soils, but also saturated and partly saturated and with flowing groundwater. And we compared Plaxis, Caesar, FLAC, and set soil and NUMGEO. So I will upload these results once I have I'm cleared to do so from the partners of that project. So there will be then a couple of more examples, especially also comparing to the industry standard.
Right, I see. Thank you. But maybe my question wasn't very well elaborated. I was thinking more about the bearing capacity below the foundation when you have the whole development of is it
Yeah, I mean, you can do that. Bearing capacity, let's say with a semi-sand model, for such simulations, I would rather maybe go to Mokulon or something like that.
Yeah.
And yeah, one can do that. You will have, as in all the other finite element simulations, the question of discretization. If you are really interested in shear bands, right? If you want to have a proper discretization of the shear bands, you will have to use a fine mesh below the foundation. But then, yes, we have done such things for foundations, right? So bearing capacity, modified cum clay. We have tested a lot of or applied it. A lot of modified cum clay for this type, because usually it is more of an interest for us for clay type soils, at least in what I have done so far. So my focus was more on that. It's a Mokulon modified cum clay, and the results there were reasonable.
all right. Thank you, Jan.
Okay, Jan, two last questions. The first one is from Cesar, and it's regarding the graphical user interface, and if it is connected to the program, meaning that any change of the code outside or in the API is reflected directly on the program immediately.
Yeah, so you mean when I'm going into that directory, I take that file and I modify something. And then if I find this modification here in my GID. So this is not the case. The reason for that is so we have contacted Simne, so the GID developers, for that. And but the problem is that they say, well, it's not that easy to do so, right? Because we have to have this two-way communication. So we are currently elaborating possibilities to do so. At least maybe to have manually a macro that you activate and then a synchronization is started. But we are still, let's say, figuring out with the people from Simne. We have asked that question, so we need to figure out what would be the best way to do so. But currently, it is not.
Okay, thanks. And
but you can always change things in that file, and you could copy it somewhere else, for example, or you could simply open the terminal and then start the simulation or the calculation of NUMGEO from here. So this file can always be used outside of GID. You can port it wherever you want. You can change things and run it, but it will not be reflected in the user interface.
Perfect, yeah, thank you. And the last question is from Jorge. He wants to ask about how would the program approach the modeling of construction stages of a tailings dam?
Yeah, so if you want to model construction stages, let's say building an embankment or excavating an excavation pit, the current procedure that you would have to follow is gravity loading or unloading. We are at the moment also implementing something that we call a model change. So you can see that it's already here. The model change allows you to change parts of your model mid-analysis. So for example, what is currently already available publicly is that you can change material model. That is, for example, maybe interesting. You could start with a simple model, Mokulon model, to model different stages in the model generation. And then, for example, for a dynamic simulation, you could switch then to a semi-sand model or something, right? So you can change material models. That is already implemented. And we are working currently at the to implement two more options. And the first option would be to add elements, and the other option would be to remove elements. And then you could, let's say, physically model excavation and build up. But at the time, with the current interface that you have here, you would increase the gravity and decrease the gravity. And if you want to excavate a material, you would just decrease the gravity and change the material to, let's say, an elastic material with a very, very low stiffness. So this is actually also what is done inside the commercial programs, just that they do it for you. But currently you have to do it, let's say, by hand. But we are working on to have, let's say, easier access to these two types of processes. Yeah.
Okay, yeah, thanks. So I think that was it for today. I want to thank you in the name of the NUMGEO and the CT300. I think this topic was for the most interest of everyone hearing you, and we hope and looking forward to collaborate again, maybe in another workshop or in a series of talks later on this same year. So thank you, Jan. Thank you, Patrick.
Yes, it was a pleasure, and yeah, feel free to reach out, right? Also, if you want to try it out and you're having some issues or so, feel free to reach out to us. Maybe it takes a day or two until we can respond, but we always respond, right? So thank you for having us.
Perfect, yeah. Thank you very much. So that was it for today, and we'll be in touch.
Yeah, so if you want, there is one question about a contact address. Yeah, you can just use the contact. So maybe I think that it should be, let me see, on if you go on the NUMGEO homepage, I think that our contacts are given there. Otherwise, it would also be fine for me if they are just shared with all of you. That would be also fine for me. So it's maybe not yeah, I don't know. Right, so you can change it. You can yeah, write it, circulate the email address. Otherwise, you can also write it here. But this is maybe not so good.
Provecho. Bueno, ya nadie viene a almorzar. No sé,
Was I muted? Okay, I'm sorry. Yeah, I just said that it would be okay for me if the organizers of that workshop today would just share my email address with you. Otherwise, you can also, I will just write it in the chat.
Yeah, we can share it in the chat.
So that would be my email address, or you write me on LinkedIn or whatever. You will also.
Jan, I think you're not sharing your screen.
I wrote the email address in the chat, so
Okay.
there it should be visible in the chat now. Sorry, I wrote it in a direct message. I'm very sorry. So let me see. I will write it at all. So now everyone should have access to it. Yeah.
Perfect, yeah. So one more favor, please, if we can just turn our cameras on to take a little picture for the publication. Por favor, si pudieron prender nuestras cámaras, los que estén disponibles.